on for the past 2 semesters, which is the temperature-controlled shower. My name is Volentine. I have 2 team members, Micheal Shoemaker and Collin. So kind of a brief introduction. Currently, when you turn on your shower, you set the knob to a position and you wait for the water to reach a comfortable temperature. You then might adjust the knob a few times. Also, as the hot water runs out, you find yourself constantly adjusting the knob. So the current standard shower is not very accurate. It's also not very precise. If hot or cold water is needed in another part of the home, like if someone flushes a toilet or turns on a sink, you might experience a surge of hot or cold water in your shower, which can be surprising and very uncomfortable. So the whole purpose of our system, which is right here, was to design a feedback system that will automatically control the hot and cold water flow when given a user input temperature. So some of our requirements: we wanted a very user-friendly interface. We wanted you to be able to just walk up, set your temperature, walk away, and come back to a shower that's ready for you. We also wanted to maintain a user input temperature within 2 degrees Fahrenheit of tolerance. We chose 2 degrees because most people can't tell the difference between 100 degrees and 102 degrees. In this way, our motors aren't constantly turning and we can keep the system rather efficient. We also want a short time for the system to reach the desired temperature from when the system is turned on. We also want some sort of visual feedback other than just numbers for the user to know if their temperature or if their shower temperature is within the allotted range. So this is our approach. The user first sets a desired temperature via a knob that's connected to an LCD. There's also a thermistor submerged in the output water. The main microcontroller receives these 2 temperatures and compares them. If they are within 2 degrees of each other, it repeats this process every 2 seconds of comparing. If they ever go out of the range, the main microcontroller tells the stepper driver to either open or close the hot or cold valves as needed. So a little bit about a thermistor. A thermistor is a device very similar to a resistor, except the resistance of it changes drastically enough with the temperature surrounding it. So what we did is we put the thermistor in a basic voltage divider and hooked it up to the main microcontroller. The main microcontroller would receive the voltage and then convert it to resistance, like I said, using a voltage divider formula. And we characterized the thermistor in a lab and gathered data from 45 degrees to 140 degrees. So more than enough range. And then the microcontroller goes into this lookup table and figures out from the resistance what the corresponding temperature is. I will pass it to Mike, who will take you through some of the system architecture.
Okay, you can see this is our system architecture. From a very top-level view, we have 2 modules. One that compares the temperature, and one that has a user interface. You can see down here, the smaller one's the user interface, and this is everything that controls the temperature. We start with the user interface. In one microcontroller, it's a AVR Atmega 168 connected to an LCD screen, the knob that Becca mentioned, and a button. The button just starts the whole process. So when you set the temperature, it sends that temperature over an RS-422 interface to the main microcontroller on the board. It is then compared with the voltage coming off of the thermistor that Becca just talked about. Compares that and also sends that temperature back so it can be displayed on the screen. Both temperatures are displayed, as you'll see here in a little bit. Also, when that happens, it sends a command to the stepper driver, which controls the motors, which turn the valves to adjust the water flow. So it will send which direction it goes and which one to turn. And then the stepper driver, these are all the AVR Atmega 168 microcontroller. There's 3 of them. And so the stepper driver then turns the motors. Once we're not done, the next slide. And we put Hall effect sensors in there with magnets on the gears. So it's kind of like a safety feature, so the motors won't turn the valves too far open and too far closed. And we put them on there in the spot where they're full open or full closed. And here's a picture of what we have here. You see up top there is our whole temperature control module, and down here is the different stages of our user interface. Starting up here, on the left here is looks kind of impressive, but we bought that in a store. It's the power supply for the whole system, 15 volts, and supplies over to our main board over here. It goes through 5-volt regulators, which power all the circuitry except for the motors. You see on the left there is the black one. is the main microcontroller. The thermistor is connected on the bottom and goes into the pipe, as you can see. See right there, the thermistors go into that pipe. It's connected to the main microcontroller. And then the main microcontroller also connects to a RJ45 port, which goes through a Cat5 cable to the interface. And right next to it is the stepper driver, which goes through these MOSFETs that he's pointing at there, which allow power to go into the motors and turn the gears and the valves. The motors are right there, and this is the gears. The valves go into the pipes. If we go down here, we have the different stages of the user interface. This one is on startup. It's white backlight, which is usually set at 90 when you turn it on. When you change it, you push the button, and it'll start adjusting. If it's green, it means the temperature's good. It's within the 2-degree tolerance that we set earlier. If it's red, the temperature's too hot. If it's blue, the temperature's colder than the desired input. And that's all for Collin. Collin will do the testing.
Okay, so when we build a device, we actually, instead of putting like a copper connector so that you would put it in a wall, we put threaded connectors so we can basically just attach it to the hot and cold water supply from a washing machine, just to make it a little bit easier. So we connected the device to the washing machine supply, and we would set an input temperature on the display, and then we would actually record the output temperatures as reported by the device on a computer, and rather subjectively with some graphs and quantitatively determine whether or not we were happy with the outputs and adjusted our algorithm from there. So here's a video of our sample. So here you can see the user turns on the device, sets a temperature by turning the knob. It's a waterproof knob. And there's a piece of acrylic over the entire thing. And then presses the button to turn on the device. So the user set it to 105. And now the device is actually going to start regulating valves, which you can see turning here. This valve is the cold valve. The stepper motors are receiving commands from the main microcontroller over the I2C connection and turning as necessary. So now you can see that the output temperature, which is the large number, is within the 2 degrees plus or minus tolerance of the desired temperature. And you'll notice that the output temperature is actually fluctuating a bit, and we'll talk about that in a minute. It's also set up so that if the output temperature rises or falls outside of the specified, like here, it'll change the backlight color for the user. And then here we can see if you adjust the desired temperature while the system's running, you can actually watch the output temperature start to drop rather quickly and then overshoot as the system tries to change outputs. So here's 2 runs of test data that we recorded using 2 separate algorithms. The first one, basically, if the temperature was outside of the given range, it would step 1 step at a time on either the hot or on the cold motor, and moving towards the direction to compensate for the difference. You can see here that we set the temperature to 104, and the average was 102.5. And then at the end, we changed the temperature to 110, where it rose to 109.5. But there is a bit of noise in the output, which we'll kind of talk about later. That was one of the bigger problems we had. And then down here, we actually used a slightly different algorithm, where if the temperature was outside of 10 degrees from the desired temperature, it would move by a larger number of steps, which resulted in a faster rise time, as you can see, to reach the desired temperature. So one of the biggest problems we ran into that we weren't quite anticipating was that when we started recording temperatures, we saw that they were bouncing around a lot. And what we actually think was happening is that our thermistor submerged in the flow was so close to the T-junction where the hot and cold flows met that the water isn't really mixed when we're probing the data. So in this sample here, what we did is we set the valves to arbitrary points and turned off the motors so that water would just flow, and then recorded the temperature for a little over a minute. And as you can see, we are seeing a lot of noise in the output. So to compensate for this, we actually started averaging temperatures over a 2-second window rather than trying to update every half second or quarter second like we were earlier. But at the same time, we wanted to keep the thermistor as close to the mix point as possible so that we could minimize the amount of time between a valve opening or closing and a change in the output temperature. So So over here we have man hours worked. Over the 2 semesters, we worked about 429 hours, and we spent $192.50 on parts. Some of the parts we did get for free, such as the stepper motors, which we estimate were probably about $15 a piece. And then Rebecca was our project manager, I was the technical manager, and then Mike was our financial manager. And we learned a number of lessons. The biggest being allowed time for unforeseen design changes. Had we had more time, we probably would have gone back and tried to move the thermistor or put some sort of mixing valve into the point where the hot and cold water meet. But as it was, we didn't have time to make this change. Also, parts should be ordered such that they do not operate near their maximum ratings. We were having a lot of problems at the beginning where our motors would source too much current and actually cause our power supply to turn off, then would immediately turn back on, so we didn't really notice it. And our microcontroller was acting really funny because it would just start the code over, and we were like, why are you doing that? And then oscilloscopes are invaluable for troubleshooting, which, had we had one on hand at the time, would have told us that our power supply was turning off. And we'd like to give a special thanks to Dr. Laurie as our faculty supervisor, and then Dr. Nelson and Dr. Cook for giving us constant feedback, and Dr. Boomeroo of the physics department, who gave us lab access so that we could characterize our thermistor months ago.